Well, thank you very much for having me. I'm really excited to be talking to you about this. This is a collaboration between the automated reasoning group in AWS and AWS Crypto and my long year collaborator, Matthias Kanwischer. So it's basically a case study in the use of automated reasoning and cryptographic engineering. So let's start by asking from the customer's perspective, what is actually good cryptographic engineering? I mean, foremost, cryptography is meant to protect the customer's privacy. So good cryptographic engineering implements the right cryptographic schemes in a secure way. But ideally, not just securely, but also somewhat fast, because as important as it is, cryptography is also some kind of computational tax, which eats away cycles that the customer would like to spend on their computational workloads. And finally, it should be somewhat agile and maintainable, because even if you have a formally verified implementation, which is super fast, but you can't make any changes, hardly anyone understands it, then down the lane, probably you get a maintainability problem with that. And kind of the thesis of my talk is that formal verification and automated reasoning more broadly, they can actually help with all of these and help bridge the tension that exists between those things. And the context of my talk is a pretty fruitful collaboration between Automated Reasoning Group and AWS Cryptography, which goes many years back, and I just want to highlight some recent achievements. We worked hard on accelerating and verifying RSA signatures on our Graviton cores, and had a blog post about that under that title. And there was also a blog post about the work we did on X25541, the elliptic curve crypto. And this talk continues that collaboration, talks about post-quantum crypto and ML-KEM specifically. So very briefly, I guess you all know that, but what is post-quantum crypto about? I mean, most secure communication relies on some sort of key agreement and some sort of authentication and digital signature scheme. And classically, we do this by a combination of RSA and elliptic curve crypto. But you know, for 30 years, it's known that a sufficiently large quantum computer is likely able to attack those things. And while there's a lot of uncertainty about when this might actually happen, if ever, it's enough uncertainty that people now for decades have been asking the question, what crypto could be used otherwise? And that process has reached an important milestone last year when NIST standardized multiple cryptographic schemes as hopefully post-quantum secure, among which ML-KEM, which is a key agreement scheme, and ML-DSA, which is a digital signature scheme. And I'm marking them with plus because it's important to note that they're not going to replace RSA and ECC anytime soon. You run them on top of RSA and ECC. And if you think back to this cryptographic tax tenet we had, it can only grow, right? The best thing we can hope for is that we make it so fast that it's basically transparent to the customer if they switch to post-quantum crypto, because the tax increase is kind of negligible. I don't have the time here, unfortunately, to say something about the math of ML-KEM. So we need to skip that. We only look at it from a computational perspective. If you want to implement ML-KEM, there are basically two components that you need to make fast. The dominant component is hashing, the SHA-3 and shake. So usually you have some kind of pure randomness seed that you feed your algorithm in the beginning, but ML-KEM relies on a lot of randomness, and this is done by taking the randomness seed, which you get, and kind of generating pseudo-random streams of byte from that. And that's done via shake. And this thing is designed so you have lots of independent randomness streams. So really the key to making ML-KEM fast from the hashing side is to kind of batch those independent randomness expansions that you have. And then on the other hand, you'd have modular arithmetic. I mean, you do arithmetic in this funny quotient polynomial ring, where the underlying arithmetic is the prime field over 3329. So you need to have fast modular arithmetic in this prime field. Then you need to do fast multiplication in this polynomial ring. That's where the number theoretic transform comes in. And then also you need to avoid modular reduction as long as you can. Typically, you see this 3329 that fits in a 16-bit word with quite a bit of slack. So if you want to add two numbers, you usually just add them, and you only reduce once you are kind of at risk of overflowing the word boundary. I mean, the details aren't terribly important here, just to give you a feeling of what are the key components to get a fast ML-KEM implementation. So what's the challenge? There's a good implementation of ML-KEM, which was actually written by the people who proposed ML-KEM, which was formerly known as Kyber. It's a C implementation. Lots of people have looked at it. It's pretty clean. So from that perspective, it's really nice. But we also have years of research on ML-KEM. How do you make this SHA-3 fast? How do you make this arithmetic fast? And yes, they come with implementations, but they are not production ready. So the challenge that we set ourselves was, can we somehow bring those things together and really come up with one implementation that's production ready, builds on the clean implementation that so many people have looked at, but also takes into account all this research. And that's our implementation, which we call ML-KEM-native. It's this join of the reference implementation and all this research, and it aims to be fast. It aims to be secure through formal verification, and it aims to be modular, maintainable through a modular architecture. And I mean, there's no one size fits all. Our implementation mainly targets application cores. So maybe if you have a microcontroller on the upper end of the microcontroller spectrum, you can still use this. If you have 500 bytes of RAM, then this is not for you, and we won't attempt that. So ML-KEM-native is an open source project, which is maintained by myself and my collaborator Matthias, and it's part of the Post-Quantum Code package. The Post-Quantum Code package is part of the Post-Quantum Crypto Alliance, which Amazon supports, and the Post-Quantum Crypto Alliance is supported by the Linux Foundation. So this kind of gives you an idea of the governance of this project. But yeah, you find it online. It's an open source project. Right. Just a minute. You can interrupt me at any time, by the way. So let's zoom into the details a little bit. How is ML-KEM-native actually structured? I said we have those two components. We have arithmetic and we have hashing. And the implementation is broadly structured along those lines. You have a hashing component, you have an arithmetic component, so that's one dimension. The other dimension is the front-end, back-end split, where the front end is completely written in C and is kind of all the logic that's not performance critical, and that's kind of fixed. And then you have the back-end, which are all the routines that are really performance sensitive and which you may implement in C, which is kind of the default, but which you may want to stub out and replace by some optimized assembly. So you see that below on the, the formatting got wrong there. On the shake side, you have basically the Ketchuk permutation is the core of shake that you need to accelerate. On the arithmetic side, you have this number theoretic transform and rejection sampling. So dedicated routines that are really worth rewriting in assembly. But and we have backends both in C and we have them in ARM and x86, and there's a work in progress backend for RISC-64. And if you don't care about the optimized assembly, you can just use it in the pure C version. Or what's common, if the library that you integrate in already has its own SHA-3 implementation, then you just don't take the one from ML-KEM-native, you plug in your own. So the whole thing is it's fairly modularly designed, so you can just pick the pieces that you care about. So let's zoom into the aspects of minimizing cryptographic tags and maintainability a little. And things get a little bit technical now. I hope you'll stick with me. So what we write as developers is clean assembly, by which I mean you write assembly where you use register aliases for variable names, and you use assembly macros to capture bits of functionality. And with this, you're still writing machine code, but it turns out to be quite readable, high-level machine code. That's what I mean by clean assembly. And those register aliases and assembly macros, those are features that are part of off-the-shelf GCC, for example. So it's code that you can run as is. And then we feed that through a super optimizer, which I wrote a few years ago, a Slothy. I'll say a bit more about that in a minute, which gives you like highly optimized assembly. And then that's somehow assembled and disassembled to give you just the rawest assembly possible, which is hopefully compatible with whatever build tool chain your target crypto library has. And the whole flow here is fully automatic. So if we want to make a change to the implementation, we change just the clean assembly, which is usually pretty straightforward because it's written in this high-level way. And then we push the button and Slothy does the optimization. So probably it's difficult to see at the end, but the details don't matter anyway. So on the left here, you see some snippet of working assembly, which makes use of register aliases, data 1, 2, 3, and assembly macros, this transpose 4 or CT butterfly. So this is part of a number theoretic transform implementation straight in assembly. But you see, it is assembly, but quite readable, but not so anymore if you feed this to Slothy, which then completely changes things in such a way that it runs fast on the target microarchitecture. And you see what comes out is completely unmaintainable. If that was what you wrote by hand, well, good luck getting that into production anywhere. But here, this is just the push of a button. So what does this Slothy thing actually do? The motivation behind Slothy is that instruction scheduling can have a significant impact on performance. So it's absolutely essential if you work in the microcontroller space. Those are usually in-order CPUs, and their instruction scheduling really can make a 2x difference if you get it right. But somewhat surprisingly, even an out-of-order CPU can benefit notably from good instruction scheduling. But this is extremely tedious and time-consuming. I literally spend weeks of my life doing this by hand, and it's, in a way, it's a nice puzzle and rewarding if it works, but it just takes a lot of time, and then you get it right for one CPU. And also what comes out of this is, as I said, completely unreadable and mangles what is conceptually separate into one big stream of instructions. And also you might spend weeks trying and find out, I can't do it better. And that's a valid outcome. It just happens. But then in a way you've just lost a lot of time. So the idea behind Slothy is to automate all of this. It's a super optimizer specifically for instruction scheduling, register allocation, and instruction scheduling across the loop boundaries, so software pipelining. And one should really distinguish this from synthesizing super optimizers, where you have like a little piece of functionality that you want to implement, and you ask the super optimizer, how can I best map that into my target architecture? Here it's different. The developer has written the instructions, and Slothy shuffles them around to just flow smoothly through the pipeline. Ideally, you would put those things together. And the way this is done is, I think, quite similar to what we heard in Andrew's talk. You formulate the optimization problem as a constraint solving problem and pass that on to a solver. And the information that you feed the tool is, well, a model of the architecture, but also a model of the target microarchitecture, where you capture exactly the things that every software optimization guide would give you: latencies, throughput, execution units. That's what Slothy knows about, and with respect to this information, it gives you the perfect assembly out. But again, the vision is that we as developers, we just maintain the clean assembly. And we published this in 2024 and got the best paper runner-up in just 2024. So another example, I gave you a flavor of the NTT. What did we do about SHA-3 and how was Slothy used in there? I mean, we target application CPUs, which are superscalar CPUs where you have lots of different execution units, which ideally you want to write your code in such a way that it keeps all those execution units busy. And if you look at SHA-3, it's lots of bit fiddling, and bit fiddling is well supported in scalar instructions, but also in vector instructions. So it's not so clear what is actually best way to implement SHA-3, which works on both of these units well. So the ideas can be implemented in such a way that we have some kind of hybrid where we use both scalar and vector units at the same time. And this is an excerpt of the software optimization guide, which would lead you to this suspicion that, it should work well on both scalar and vector, because you get the information about how many vector units I have, how many scalar units do I have for in those cases, And you would also find out, oh, on some CPUs I even have special SHA-3 instructions, which sadly are only supported on one of the units. So if you just use those SHA-3 instructions, actually what you get is slower than if you're not using them. It's a bit sad. Anyway, so what we do is we write a batched version of Keccak where we compute 4 instances of Keccak at once. And 2 of them, the yellow ones, are written in scalar instructions. And 2 of them, the red ones, are using neon, like vector instructions. And we write this completely sequentially, which is quite doable manually. And then we feed that through Slothy, which does the zipping together. So Slothy then makes it so that those instructions which are completely separate on the left-hand side, they get zipped together in the final assembly, where you see indicated by colors here. The yellow instructions are scalar instructions, the red instructions are neon, and the blue are SHA-3. And again, what comes out is really fast, but you wouldn't want to write this by hand and not maintain that. But you don't have to, because what you write is the thing on the left. And well, you do all those tricks, and what you get is an implementation that's 3 to 3.5 times faster than it was before. So let's revisit our goal: minimizing cryptographic text and maximizing agility. Have we achieved that? I think we have achieved the maintainability thing, because what we write is just a clean assembly that's pretty maintainable. But have we achieved minimizing cryptographic text? That's not so clear. Yes, this is very, very fast code. And yes, the Slothy thing gives you some transparency in how you get the code, but still not formally verified. And you might still not feel comfortable actually deploying that code. And code that's not deployed, then yeah, maybe fast, but it's worth nothing. So it's going in a good direction, but without formal verification, you might still not have enough confidence to actually use that code. So what did we do about formal verification? I'm going back to this overview. All the C components we've verified with CBMC, the C-bounded model checker, and I'll say more about in a minute what that entails. And all the AH64 assembly we've verified using HOL-Light, John Harrison's theorem prover. So then a few slides now on showing you what that looks like in more detail. So what did we do about C? What we're aiming for with CBMC is memory safety and type safety, whereby type safety I specifically mean no arithmetic overflow. And I mean, we heard it earlier, I'd rather have something good now than something perfect later. What we don't try here is full functional correctness. We're aiming for those 2 types of safety properties. And no overflow is a really interesting property in the ML-KEM context, because you do all this lazy reduction where you kind of add as long as you can, and then just before you're about to overflow, you introduce a reduction. And CBMC will guarantee you that you got that right. Yeah, we cover all the C code, hundreds of functions. It's done through in-source annotations, which are pretty readable and maintainable. I'll give you an example in a second. And this runs on every change you make to the code, and it takes 15 minutes. So it's very reasonable to have that in CI. And I've worked with a number of people who haven't used CBMC before, who now regularly do. It's very easy to learn and very intuitive. So again, I think that might be a bit tricky to read at the back. I'm sorry for that. But just to give you a flavor of what that looks like, you see a function declaration here, whatever arithmetic that does. And in this __ contract annotation, you have the CBMC contract, which if you don't use CBMC will just unfold to nothing. So you can still compile it without CBMC. And you have preconditions on kind of memory validity and non-aliasing. And then you have some bounds conditions, yeah, saying what the arithmetic bounds on the inputs. And then in implementation, similar, if you have a loop, you have this __ loop thing where you can say what the loop invariant is. And if you call another function which already has its contract specified improved before, then CBMC will invoke that by contract rather than inlining, of course. And this way, you bootstrap from the leaf functions to the top-level API of ML-KEM-native those CBMC proofs. And yeah, I think it's a bit more than 100 overall. But really this is all. Those are the annotations that you provide. The contract and the invariance. I don't think we ever need assertions to kind of guide the prover through the proof. It's really extremely convenient and easy to learn. What do we do about HOL-Light? That's a bit different. Here we do aim for full functional correctness of the ARM assembly and not actually the assembly of the resulting assembled object code. And we are covering all the assembly kernels that we have in ML-KEM-native. And this is done through manual interactive proof using the HOL-Light theorem prover and the S2N BigNum verification infrastructure for HOL-Light. And again, this is fast-ish enough that you can run it whenever you make a change. So it takes about 1.5 hours. We only run this if we actually touch the file that's being checked. But it's okay. It's good enough for us. So what does that look like? We had this assembly flow before. The assembly file gets fed into the assembler, which gives you an object file. Then the proof author writes this interactive proof, which then with the object file gets fed into HOL-Light, and HOL-Light says yes or no. That's a fair proof. And then we also take those specs that are written in HOL-Light and we translate them to CBMC specs manually. And that's what the CBMC proofs at the lowest level then build on. Yeah, same problem as before. This is a HOL-Light spec just to give you a flavor of what that looks like. There are aliasing constraints, there are input bounds, there's the description of what has happened functionally, and there are some output bounds. So you can look at that in more detail if you like it, just to give you a sense. But in particular, you see there is this full functional specification of what's going on, which you didn't have on the CBMC side, which you see above. It's a manually translated CBMC spec, where you still have the bounds, you still have validity constraints on the memory, but you don't have the full functional behavior anymore. And that's then what the CBMC builds on. And we need to make sure manually so far that this isn't going out of sync. What about side channel attacks? So all code in ML-KEM-native is written with constant time in mind. So what does that actually mean? We don't have secret dependent branches or memory accesses. We don't feed secret data into variable time instructions like a division. And wherever there's risk that the compiler, even though we didn't write a branch, would add a branch, and we don't want that, we use kind of barriers to prevent to kind of block the value reasoning in the compiler. And we use valgrind to test some of those things. So valgrind would flag secret dependent branches, memory accesses, and also secret dependent divisions, for example. So what does that look like in the code? You will probably know every crypto library needs a constant time memory compare, because normal memory compare would kind of bail out as soon as it finds a difference and thereby leak something about the data that's being compared. And then you jump through all sorts of hoops to make this constant time. But what CBMC gives us here is actually quite nice, because while normally we don't specify functional behavior with CBMC, for simple functions as this, you can actually do that. So in the green line at the top, you see the return value being 0 is the same as the inputs being element-wise equal. So here we have a functional spec in CBMC saying this is actually a mem-compare implementation on the functional level, even though it jumps through all those hoops to be constant time. Right, almost at the end. Where do we use ML-KEM-native? ML-KEM-native, the pure C version so far, is integrated into AWS's crypto library, AWS-LC. And AWS-LC has bindings into lots of different languages like Rust and Python, and from there gets fed into higher level applications or libraries, Russells, S2N Quick, S2N TLS. So this way, ML-KEM-native finds its way into lots of applications. And it's work in progress to extend the integration to those ARM64 and x86 backends. So we kind of cleared the technical hurdle for ARM because we've done all the functional correctness proofs, and that was our bar. So I'm in the process of integrating that, and x86, that's work for the future. And yeah, it's also integrated into the Open Quantum Safe post-quantum crypto library. Yeah, and because it was quite a successful project, now we're doing it all again, or Rod's doing it all again for ML-DSA. So as I said, ML-DSA is the digital signature post-quantum standard, and we are following exactly the same approach with as with ML-KEM-native to develop this ML-DSA native to come up with the modular, fast, and verified ML-DSA implementation. So reflecting on our tenets in the beginning, how did we achieve that? Of course, formal verification gives you like reproducible claims of safety and correctness. That's kind of the main gain one would associate with formal verification at first. But it also helped us to actually get those highly optimized implementations into production, because otherwise we would have had a really hard time convincing yourself or others that they're actually trustworthy. In that sense, formal is fast, because without the formal verification, you might not be able to deploy whatever clever thing you have come up with. And on the maintainability front, yeah, we've seen that through Slothy, despite all those optimizations, what we as developers need to audit and maintain is just a fairly high-level piece of assembly. So yeah, automated reasoning and formal verification really help us here to put all those things together and end up with a fast and verified and usable crypto library. Yeah, and that's it.
Are there any questions from the audience?
Thanks for the talk. Sorry if it's a very naive question from a programming language person, but it seems that what you're currently missing is a nice input language that could replace your scary to me high-level assembly, because your assembly is non-portable and the things that you do seem to be, you don't need a lot of kind of properties of language. So I could imagine that you could define a nice function language, you can specify some properties and then pre-generate all the invariants that you have to write by hands and blah, blah, blah. So is there any problem with this mindset or view? So you do a lot of manual work that it seems that you could have automated.
I mean, yes, you're right. It is still a fair amount of work to write all this assembly. And ideally, one would have some slightly higher level language from which you go to all the assembly. On the other hand, the instruction set architectures are quite different. So the way you would implement a number theoretic transform on Neon is different than you would do on AVX2, say. So coming up with a high level language and a compiler, which gives you the optimal result, is at least not straightforward. I mean, there are higher level languages like Jasmine, which you can use to come up with formally verified and fast implementations. And there's, under the post-quantum code package, there's this ML-KEM libjade, which uses the Jasmine programming language as an alternative, which I think goes in the direction of what you are asking. But yeah, for us, we do write the clean assembly by hand, and so far do not intend to step up one level.
Great, thank you. We have time for one more question, a quick one. Francois.
Yeah, I can talk with Hanno and you about Jasmine in the break as well. My question was more about the maintainability of the HOL-Light proof, given that it ranges over an object that's generated during CI.
Oh yeah, I should really have said that. So the nice thing about this application in particular is that the loops are all bounded and the proofs are fast enough that you can just unroll the whole code in symbolic execution and then do the proof on the resulting humongous expression, which has the benefit that the proof is completely agnostic to the things that Slothy does. So normally, if you had a proof which reasoned by invariant and then Slothy comes along and muddles up all the loop invariants, interleaves the different loop iterations, you would need to write a completely new proof, and coming up with the invariant would be really hard. But because here everything is bounded enough, you can just unroll it. You write one HOL-Light proof, and it's at least agnostic to reorderings. That doesn't mean if you make any algorithmic changes, you would need to touch it. But so far, we have found this actually quite workable, even in the face of occasional changes to the assembly. And also on the CBMC side, we don't have any issues with proof brittleness, which was really nice to see.
Okay, I think we might have to stop there in the interest of time. Thank you, Hanno.